Hello. So today we are going to continue with chapter 5, that is nuclear chemistry. The only thing that you need to remember for this chapter is what I explained in the previous chapter, that if you have any element, the lower left is going to be called the atomic number and the upper left is going to be called the mass number. Okay, that's the only thing that you need to remember for this chapter. So first of all, let's start what is a radioactive isotope. Last class we said that a radioactive isotope, no, not a radioactive isotope, but last class we said that an isotope is compounds that have, or no compounds, atoms or elements that has the same Z but different mass. Okay, by being the same Z, it means that they are the same element. Okay, so isotopes are the same element, but they have different A. Okay, and a radioactive isotope has an unstable nucleus and usually has an atomic number above 20, emits radiation to become more stable. Okay, so that one is an important point. Emits radiation to become more stable. Okay, can be one or more of the isotope of an element. Okay, this is what we talked last class, that there are elements and those elements have several isotopes. Okay, the way how we are going to write this isotope is in two ways. For example, like this, okay, or like this. Okay, the second way, this way is a little bit more difficult, especially if you are in a paper. Unless you are writing with pen, then this way is easy. But if you have to do by computer or by any type of analytical stuff, it's much better to do just like this or like that. Okay, so now I want you to remember that the mass number is not the decimals in the bottom, okay, that is in the periodic table. That's atomic mass. This is mass number. Mass number, as I told you, is given only by neutrons. Sorry, this is not ink. Is given by protons plus neutrons. Okay, and most of the time that number must to be given. Okay, most of the time it must to be given because you don't know. And as I told you last class, probably when you round the atomic mass, you can get the mass of or you can get the most abundant isotope. Okay, so now let me tell you quickly, before I continue with these types of radiation, a story that, let me create a new page here. There was a scientist called Becquerel. Okay, I think his name was Henry, and his last name is Henry Becquerel. Henry Becquerel was studying fluorescence and phosphorescence. So what he did is that he looked for different kinds of rocks in the mines, and whenever he find one, he charged the rock. This is my rock, and he charged the rock under the sun. Okay, for several hours. After he finished charging, then he wrapped the rock in photograph paper. Okay, that's photograph paper. The opposite, photograph paper. And after, put it in the dark. and put it in the dark. And later he's going to check and he's going to realize that a picture of the rock will appear in the photograph paper. Okay, so the rock took his own selfie. Okay, so that's what he commonly does. And if the rock takes the picture, means that rock was fluorescence. But if the rock nothing appears, means that rock is not fluorescence. Okay, that was what he commonly studied. One day this Becquerel found a rock of uranium. Okay, he tried to put the rock of uranium under the sun, but what happened, it was raining that day. Okay, it was raining, so he cannot do the experiment. So what he did is he just put the rock in the photograph paper and keep it in his drawer until keep it in the dark until the next time. Okay, 4 days later he realized that uranium took a picture of himself. Okay, took a selfie. The question that he did is why. Okay, he never charged uranium. So what he believed is that uranium is kind of this element like radium that emits some kind of energy. Okay, and that kind of energy is called radioactivity because they found that radium emits some kind of energy, and they didn't know what it is, but they know it comes from radium, so that's why they call it radioactivity. Okay, so he started believing that uranium is like radium, so it's emitting his own radioactivity. To verify that, he took the rock to the Curie couple, okay, the Curie couple, Pierre and Marie Curie, okay, they are famous couple, especially Marie, that she got 2 Nobel Prizes in chemistry because of in physics, because of the radiation. Okay, so what Marie did is, so what this couple did is, they put the uranium in a radio box. So sorry, not radio, sorry, in a lead box. So this is a lead box. Okay, this is a lead. In chemistry, lead is written as Pb. This is a lead box. Lead box is the only type of metal that can hold the radioactivity. Otherwise, the radioactivity is going to come out. Okay? And what this couple did is they put an electric field. Okay, this is an electric field or electricity. Okay, and what they did is, okay, this box, this opening is just to reorient the radioactivity. So they want to send the radioactivity, let me change color here. So they want to send the radioactivity just redirected towards the electric field. And what they saw is that some of them were attracted to the negative side. Okay, those rays that were attracted to the negative side, they call them alpha rays. Okay, and those alpha rays, because they were attracted to the negative, according to physics, right, opposite charges attract each other, so those alpha rays are positive. Then other group were attracted to the positive side, and those were called beta rays. Okay, and because they were attracted to the negative side, so these rays were negative. Okay, and finally another group of rays, they just went straight. They were not attracted to anything, so they were called gamma rays. And gamma rays is neutral. They have a charge of 0. Okay? Okay, so that's how this radioactivity started. Okay? Now, types of radiation. Okay, so what you need to learn here are the particles that produce the radiation. We already talked about the first one, alpha particles, that they are positive charges. Okay, they are positive charges. But these positive rays, later they find out that the nucleus is exactly the same as the helium nucleus. So what that means, that these alpha particles has 2 protons and 2 neutrons. That means a total mass of 4. That's why there are 2 ways of writing this alpha particle, as alpha or helium 4-2. Okay? Then we have beta particles. Beta particles has a negative charge. And as you know, the only thing that has a negative charge is an electron. That is why this is written as a beta, because it doesn't have protons. That means it's negative. It's going to be a -1 here. And because it's not a neutron, it's not a proton, it's going to become here. Or just electron -1, 0. So those are the 2 ways how commonly we write the beta ray. And these are the 2 ways how we write the alpha ray. Okay? These particles has to be memorized. Okay? Now, the next one, they find out also that there are something that looks like an electron, but it has a positive charge. And they name it positron. You see, positron means positive electron. And the positive electron is written as electron. Now this guy is positive, but it's not proton, it's not neutron. Or if you want to use the beta symbol, you can use beta, positive, 0. And that is called the positron. Okay? The gamma ray, as I told you, is the neutral ones. And those are the most powerful and dangerous. Okay? You have to be careful with these guys. These guys are really, really dangerous, and most of the mortality by radiation is because of the gamma rays. Okay, the gamma rays is the one that gives you the cancer, mutations, and kill you. Okay, so for the gamma, we are just going to write a gamma. Let me write it. Let me just handwrite it. A gamma 0 because it doesn't have any charge, it's neutral, and 0 because it doesn't have any mass. Okay, and because it's pure energy, that's why it's so fast. Then the proton that we talked last class, right? The proton that is also called Z, that is number of protons, right? We have 2 ways to write it. Proton 1,1 or hydrogen 1,1, because they find out that the proton is kind of the same atom as the hydrogen. Okay? Without the electron, because hydrogen have an electron. If you remove the electron, because we are talking about the nucleus of hydrogen, then is 1,1p or 1,1h. Okay? And finally, we have the neutron that is written as this. Okay? Okay, so not this one, don't use this one. Always use your numbers next to the side. So those are the 6 particles that you have to memorize for this chapter. Let's start again. Alpha, beta, positron, gamma, proton, and neutron. Okay, those are the 6. Okay, so let's continue. Biological effects of radiation. When radiation strikes molecules, electrons may be knocked away. Okay? So, example, when gamma rays hits water, electrons of the water goes away, making some positive radical of water. Okay? And remember, your body is full of water. So when you are exposed to radiation, a lot of water in your body becomes this positive water, and that positive water start causing undesirable chemical reactions damaging cells and also reacting with your DNA, and that's why you hear that radiation produce mutations, because the water is kind of messing with the DNA. Okay, commonly they don't do nothing. They actually later we are going to see that they make nice bonding between them, but this is not regular water. This water lost an electron and is craving to react. Okay. Okay, how can you protect from radiation? Easy. By using paper and regular clothing, you are going to just protect against alpha particles. If you're wearing a lab coat or gloves, that's enough for beta particles. If you start using a lead shield, like when you go to the dentist to take an x-ray and the dentist gives you this heavy apron, that is a lead shield. Okay, a lead shield or thick concrete wall is going to protect you against gamma ray. Okay, additional, you need to limit the amount of time that you are exposed to radiation, and also increase the distance from you to the source of the radiation. Okay, so be careful. For example, in the 80s was a huge accident. A nuclear plant called Chernobyl exploded in Russia. Okay, that explosion made a huge environmental problems. People believed that it was some kind of fireworks. So a lot of people that live closer to the nuclear reactor went to a bridge to observe those fireworks. The problem is, first, the bridge was very close to the nuclear reactor. Second, they stay long time observing those fireworks. But in reality, they were not fireworks. It was the nuclear reactor that was exploding. All those people on that bridge died. Okay? So they don't die at that moment. But as the weeks were passing by, they start decomposing it little by little, and it's a really, really painful death. Okay? Okay. What shielding is required to protect from the forms of radiation? Well, I cannot hear here, but you protect alpha by just using a paper or a cloth, just regular cloth. How you protect from gamma radiation? By using a lead apron or concrete. Okay? Which form of radiation emitted has a number of 0, mass number of 0, and a positive charge? Okay, so that means if the mass is 0, means it cannot be a proton, it cannot be a neutron, so that means it has to be an electron. Okay? And because it's positive 1, means it's not a regular electron, it's a positron. Okay? Nuclear reactions. There are two types of nuclear reactions. Okay? Let me write here. There are two types. The first nuclear reaction is called decay or decomposition. Okay? Some people call it also emission. This is natural. Okay. The second type of reaction, okay, is man-made. Okay, and that man-made reaction is when one element is stable, and like here, actually this is an example of actually man-made is called transmutation. Okay, how you recognize both? This one is just a natural decomposition, means you have an element and natural the element decompose in something else plus any of those particles. Oh, I cannot write here, I cannot write outside of this, so let me write here. The element will decompose between the, so the element, you put the element and it's going to decompose in something else plus one of these particle or 6 particles that we were talking about. Okay, that's the shape. And as you can see here, this thing doesn't look anything at all. Okay, now a transmutation is we are going to force an element that is stable to become something else. For example, this element here, A, is very stable. Okay, is very stable, and we are going to bombard, okay, or attack that element with one of those particles that we saw to produce something else plus more particles. Okay, and this is the shape of this reaction. Okay, as you can see, it's easy to recognize. One is just one element that decomposes into something else. This is 2 of them. And clearly you can see that this example here is an example of transmutation. This is your element that is stable. This is going to be bombarded by the particles of helium or alpha ray, right? These guys are alpha. And after they are bombarded, they are going to become this nitrogen, that is a different element, plus another particle that in this case is a neutron. Okay? Now, before I continue with this, let me tell you what is the main rule of nuclear equations. Let me create another page here. Okay. Nuclear reactions, it doesn't matter if it's the natural or the transmutation, you are going to have something like this. Okay? How do you know it is correct? Because let's call this A, Z, I don't know, A1, Z1, A2, Z2, A3, Z3. Oh, wait, my bad. Okay, sorry, I make a mistake here. That's my bad. Okay. Oh, okay, I'm going to write again. Okay, let's see this here. Okay, so again, A, B, C, D. Okay, so A is going to be, this is Z and A. This is going to be C1, A1. This is going to be Z2, A2. And this is going to be Z3, A3. What you have to verify, and this verification is called balancing, okay, is that the number of A's in the reactants, okay, that means in the left side, has to be equal to the number of masses in the products. Not only that, you also has to verify that that atomic number in the reactants or left side is equal to the atomic number in the right side or products. If you are able to verify both cases, then you can say your equation is balanced and is correct. Okay? Let's test it with this equation that is here. Let's add the masses. Okay, so let's check for masses first. In the left side, I have this 4 and I have this 10. So 4 plus 10. In the right side, I have this 13 and this 1. 13 plus 1. Total 14 equal 14. Mass was verified. Okay, let me change color. Now let's verify for Z. Okay, so let's say Z. So my Z is the ones in the bottom. So in the right, I have 2 plus 5. Sorry, in the left. And in the right, I have 7 plus 0. So that means 7 equal to 7. And the Z was verified. So this equation is correct. Okay? Okay. Let's continue. Okay, now let's start talking about the decays. The decays, there are some decays that are more important. Now, what happened here? Why this is here? Let's see, there's this. I don't know. Oh, I think it has to do with this. Okay, anyway. Yeah. Alpha decay. Okay. As the name says, alpha decay. I told you decay means emission, means decomposition. So that means you are going to take element A, and element A is going to become something else, and alpha will be released. Okay? For example, here you have uranium. You have uranium here, and you see uranium becomes thorium plus something else. Okay, you have to double check. 238, 234 plus 4, 238, 92, 90 plus 2, 92. Okay, that equation is correct. The thing is, I'm not going to give you the equation. You have to do it by yourself. For example, I say, can you write the alpha decay, okay, of, let me pick any element. Let me see. I'm just creating here a number. Let me say cobalt. Okay, let me say cobalt 60. That's what I'm going to ask you in the exam. So what you have to do is, okay, alpha decomposition means cobalt 60. Look at the periodic table. This value is 27. This is going to decompose in something else, and is going to produce also an alpha. And as you know, alpha is for helium 42. And now you are going to balance, and you are going to say, let me change color here. 27 in this side. In the other side, there is a 2. So that means I need a 25 here. If you look at in the periodic table, the 25 is manganese. Okay, now in the top, this is 60, this is 4, so that I need a 56. Okay, so here it is. 56 plus 4, 60, 25 plus 2, 27, and that's your alpha decay of cobalt. And you can practice with any element in the periodic table. Okay, For example, here. Write an equation that do the alpha decay of radon 22. Okay, so radon 222. Let me see radon. Radon is in the periodic table 86. Okay, now it says it's an alpha decay, so that means it's going to produce alpha plus something else. Now let's complete this, and we say here is 86, so that means here has to be 84. 84 plus 2, 86. And who is 84? 84 is polonium. No, polonium? Yes, polonium. Okay, that's what you have to check in your periodic table. And here is going to be 118. So 118 plus 4, no, sorry, 218. 218 plus 4, 222. 84 plus 2, 86, and this is your equation for the alpha decay of radon 222. Okay? Beta decay, the same concept. A is going to decompose and produce something else plus a beta or electron. Okay, now you can see here the carbon decomposes into nitrogen plus the carbon decomposes into nitrogen plus a electron. Okay, double check, 14 on the top, 14 plus 0, 14, 6 on the bottom, 7 minus 1, 6. Okay, same example. Let's do again. Now I want you to write the beta decay of cobalt 60. Okay, same example that we did for alpha. Okay, so cobalt 60 27 is going to decompose something else plus a beta ray or electron, and this is going to produce, okay, 27. This is minus 1, so that means this has to be 28, because 28 minus 1 is 27, and this is going to stay at 60. If you look in the periodic table, who is 28? 28 is nickel. Okay, and this is your beta decay of cobalt 60. Oh, I have another problem here. Write the beta decay of potassium. Okay, potassium 42. You look at the periodic table, potassium is 19. Okay, now potassium is going to decompose, have a beta decay. Okay, plus, okay, this is going to be 20, and 20 is calcium, and in the top 42. Okay, perfect. You see, this chapter is really easy. Write the nuclear equation for beta and alpha for cobalt 60. Actually, we already did that. Just check the 2 slides previous to this, okay? Or actually, let me just erase this. Yeah, let me just erase this. Let me leave it like that, so you can now it's time for you to do it by yourself. Okay, do it by yourself, and you can verify your answers with what we just did here. Okay, now we have positron emission. Okay, positron emission is the same concept. Okay, what is this? Okay, this is wrong. This is wrong. Can I move this? Can I move this guy? No, it doesn't let me move. Okay, so it doesn't let me move, so forget about it. So this gamma radiation should not be here. Okay, this is only to tell you how the positron was created. Okay, how a positive electron is created. So a proton in the nucleus becomes a neutron, and that is going to produce a positive electron. Okay, but so you don't need, this is just for your information. A positron emission is when a compound called A is going to decompose in something else. By this time, is going to produce a positron. Okay? Example, we have here manganese 4925, okay, decomposing the positron. To become 25, it has to be 24, and that's the chromium, okay? And we balance the top. Let's do the same cobalt, the cobalt 60 that we were doing. Okay, now this time is going to decompose, it's going to emit or decompose into a positron, and this is going to be 26, and 26 is iron, and this is 60. So 26 plus 1, 27, 60 plus 0, 60, and that's the positron emission. The same way we have also, and let me add maybe a page here. No, actually here, let me add a page. Okay, there is, and this is the what we erase. There is also the gamma decay or gamma emission. That means that one compound is going to decompose into the same compound and is going to emit a lot of energy as gamma array. But you might tell me, but this is not the same element. What is the point? The thing is, this guy was super unstable and super stressed. That's why some people call it kind of the metastable. Okay, imagine when you are under stress, right? There is one point that you cannot hold it anymore and you explode. So the same. So this guy, this A here, was super stressed, and somehow I cannot hold it anymore and it explode, and that explode is going to produce a lot of gamma ray. Okay, typical example, kind of the uranium, right? Uranium 92. Let me see what you have for uranium. Let's say 240. Okay, this is just okay. So, but this is metastable. I mean that uranium is kind of unstable right now, so it's going to explode into the same uranium plus gamma ray, that is a lot of energy. Okay, now this is the transmutation that I was talking about. This is the man-made reactions. This is the equation that we already see, that it has to be a stable nucleus that we are going to bombard with alpha particles, and it's going to produce a new nucleus plus some neutrons. Okay, here says complete. Okay, who is the guy in the middle? Okay, I have, so in the left is, let's check these, 0 plus 27. In the right is 2 plus something else. So this is 27, this is 2 plus, and you can see this guy is 25. Okay, 25 is going to be manganese. Amen, manganese. Okay, now in the top, let's check the A's. We have 1 plus 59, and in this side we have X plus 4. So this is 60, right? So X is 56. So this guy is going to be 56. Okay, now let's verify. 0 plus 27, 27, 25 plus 2, 27. In the top, 1 plus 59, 60, 56 plus 4, 60, and your equation is balanced. Okay, now how you measure radiation? You measure radiation by using something called a Geiger counter. Okay, this is the one that you see in the movies, that they go to a place that is exposed with radioactivity, and they put that thing close to an object, and that thing and that equipment start vibrating and making noises. Okay, that's a Geiger counting. So the Geiger counter, what it does is detects beta and gamma radiation. Okay, And okay, so in reality is electrical equipment that what it does is somehow the radiation is going to create an electrical current, and that electrical current is going to make this thing make noises or vibrate. Okay, units of radiation, there are 6 units. You might say it's a lot, but not. Actually, in reality, there is 3, where the Curie is kind of the same thing as the Becquerel. Remember, we were talking about the Becquerel that was studying phosphorescence, and he gave his stone to Curie. Okay, so now the unit Curie is going to be similar to the Becquerel. The rad is going to be very similar to the ray, to the gray, not ray, gray. And finally, the rem is going to be very similar to the sievert. Okay, what is the difference between is that the 3 on the top is just imperial system, while the 3 in the barrel is international system or metric system. That's the only difference. So the only difference is that the Curie, the rat, and the rem are the imperial system, and the Becquerel, the gray, and the sievert are the metric or international system. Okay, let me put again international system. That's the metric. Okay, metric. Okay, now what they study. The Curie and the sievert measures radioactivity. Okay, radioactivity. Okay, just to be simple, radioactivity, and that's what this machine measures. Okay, by measuring in Curies or Becquerels, you can measure how much radioactivity one object has, or how much radioactivity are in the air. Okay, now what the rem and the rat and the gray measure. The rat measure the radiation absorbed by the body of the tissue. Means you were already exposed, you didn't know that place has radioactivity. Now they are going to measure how much radiation is in your tissues, and that is going to be in rat or gray units. Okay, and finally the rem and the sievert, they are going to measure the biological damage. So that means you were exposed to radioactivity, your tissues already absorb radiation, but that radiation inside your tissues are destroying your cells. So how much it was destroyed is going to be in rem or sievert units. Okay? Radiation sickness. Exposure to radiation of less than 25 rem is usually not detected. Whole body exposure of 1 sievert produces temporary decrease in the number of white blood cells. That means your immune system is start being attacked. Exposure to radiation greater than 1 sievert is going to be cause radiation sickness. That's the one where you start losing hair and start puking like chemotherapy. Okay, LD50 means the lethal dose 50, means the how much of a poison you need to kill 50% of the population. Okay, those are pharmacological terms. Okay, now for people whose body radiation of 6 sievert or greater would be fatal within a few weeks, and that's what happened to the people that were in Chernobyl. Okay, they lost. Okay, they died. All of them died, but they didn't die instantly. they died in the following weeks, and it was a painful death, as I said. Okay. Half-life. Half-life means how much do you need, no you, the element, how much the element needs to lose half of its concentration, okay, or half of its level. As you can see here, right now you have 20 milligrams of iodine. After one half-life, you are going to have the half. After the second half-life, you are going to have the other half. After another half-life, you are going to have another half. Okay? And that's important to know when you are going to go back to a place that was exposed to radiation. For example, if you go to a place where there is 20 grams of one radioactive compound, and you have to wait 20 years because that's the half-life, means in 20 years those 20 grams becomes 10 grams. I'm assuming 10 grams is still dangerous, so you have to wait another 20 years for those 10 grams to become 5. And then you might need to wait another 20 years for those 5 grams becomes 20.5 grams. And then probably 20 years for those 2.5 to become 125, and so on until the radiation is not dangerous anymore. So just in this example, 20 years plus 20 years plus 20 years plus 20 years, already 80 years pass, and we cannot go back to that place. Okay, it's just an example. Okay, so that's the half-life. You can see here, amount of iodine 131, okay, and it go from half-life, what is this? This is the same iodine here, 131, yeah, so it's, it doesn't say how much it is, but yeah, here you can see, okay, this is the first half-life. Oh, it is 8 years, okay, the half-life here is 8 years. So after 8 years, the 20 became 10. Another 8 years, the 10 becomes 5. Another 8 years, the 5 becomes 2.5. Another 8 years, the 2.5 becomes 125. Another year probably 0.65 probably, okay? So, and so on, okay? So 8 years here, no, days, no years, sorry, days, okay, 8 days. And we have a problem. P32 is a radioisotope used to treat leukemia, and it has a half-life of 14.3 days. If the sample contains 8 milligrams of phosphor, how many milligrams of this phosphor 32 remains in 42.9 days? Okay, so we are going to start with the first of all, we want to know how many half-lives, okay? And that's the first question that you should ask. How many half-lives? Okay, so to find that, you are going to divide the total time, 42.9 days, over the half-life, 14.3 days. And I'm guessing that's 3, right? So let me do that in my calculator. Yeah, that's 3. That's 3 half-lives. Okay, so that means if at the beginning we have 8 milligrams, after my first half-life, I'm going to have 4 milligrams. Then I'm going to have a second half-life, and it's going to become 2 milligrams. And finally, I'm going to have my third half-life, and it's going to become 1 milligram. So that means after 42.9 days, I have left still 1 milligrams of that phosphor 32 in your body. Okay? Because as you know, as I said here, the exposure to radiation start producing temporary decrease in the number of white blood cells and cause radiation sickness. For that reason, when you have some kind of radiation treatment, you don't want big half-life. You always want short half-life, okay? Short half-life. Imagine this person has leukemia, is exposed to phosphor 32, and the half-life is 14.3 days. That means 14.3 days that person is going to suffering. But not only 14, in this case 42.9, and still there is 1 milligram of radiation left in their bodies. Okay? This is just to show you example of medical isotopes. As I told you, all those medical isotopes has very short half-life in the days or in the hours. Okay? I have another problem here. The half-life of, okay, how many? 60 more in 26 hours. So we do the same. How many half-lives? So we took the total time, we take the total time over the half-life, and that's 2 half-life. So that means if you start from 64 milligrams and it undergoes 1 half-life, this is going to become 32 milligrams, but you don't want 1, you want 2. And the second half-life is going to be 16 milligrams, and your answer is B. Okay? Okay, now for radioactivity, we use radioactivity for medical imaging. Okay, for the people that want to be medical image. I know all of you want to be nursing, but probably some of you will end up working with some imaging equipments. Okay, so those imaging use, some of them use radiation, not all of them. Okay, how they work? They work by each organ. Okay, each organ has affinity for one element. For example, the thyroid has affinity for iodine. And that's one of the reasons why it's important to eat iodide salt instead of just pure salt. Because the iodide goes to your thyroid, and that's how thyroid works. You need iodine for your thyroid to work fine. Okay? Now, so you need iodide. And let's imagine this is your thyroid. Okay, this thing is your thyroid here. So the iodide that you eat, it enters into the organ and stays there. And while that iodine is there, your organ is working fine. What radioactivity medicine does, or radiation medicine does, instead of that iodine, they are going to put an isotope of iodine. For example, the 131 that we were talking in the previous example. This iodine 131 is going to kick out the regular iodine and is going to take the position. Your thyroid don't care, because your thyroid is recognizing that it's iodine. The only difference that this iodine is going to start emitting radiation. And eye scanner is going to capture that radiation and is going to produce the picture of your thyroid. Okay? So what I explain is here, radioisotope with short half-lives are used in nuclear medicine. Okay? And what they are going to use elements that have the same chemistry in the body as these non-radioactive elements. Okay? And this radiation that they kick out is going to be used to get the picture of the organ. Okay? So here you can see a lot of isotopes. Take a look at this. Everybody has short half-life. This is the type of radiation, and this is for why it is good. For example, the iodine 131, you see there is thyroid here, even iodine 123, there is thyroid here. So that's why, because the thyroid likes the iodine, okay? And that is when you use these scanners with radioisotopes. Another example. So how do you know if you are sick or not? Because areas of decreased or increased radiation can indicate the presence of a medical problem, okay? This is another example, the positron emission tomography for the brain. So what they give you is fluorine. So that's why people say fluorine is good for the brain, but they kick out that fluorine, will enter this fluorine there, and that fluorine is going to go a positron emission, you see? It's going to decomposing something else in your brain, and it's going to emit this positron. That's why it's called the positron emission. And with that emission, we are going to do the picture or the plaque. Okay, now the only machine that doesn't use radiation is MRI. MRI is not radiation. MRI use magnetic fields, means it use a magnet. Okay, so that's what MRI is. Okay, I leave this for you to read more. Okay, so what they use is magnets to produce magnetic strong fields. Which of the following isotopes are likely to be used in nuclear medicine? Remember, short half-life. Days, okay, years, you don't want years. Days, oh, but this is much better. Hours, okay? Now, nuclear fission. Nuclear fission is when you break one huge nucleus into several pieces, okay, like this example, and breaking this is going to produce large amounts of energy. For example, here, let's forget this, let's just go straight to this. Okay, so this uranium is happy, okay, this uranium is happy there, and suddenly comes this neutron, and this neutron is going to attack this uranium and is going to break the uranium in two. So it's going to break it in krypton and barium, and here you can see 36 of these 92 electrons becomes krypton and the other 56 becomes barium, okay? And you see, that's how it breaks. The big uranium now became two smaller nucleus, plus more neutrons. The problem here is that the reaction was a start from a nucleus. Neutron. The neutron started the reaction, and the product produced more neutrons. And this is a problem. Why? Because those nucleus are going to go back to the beginning, are going to continue reacting the uraniums. So go to the beginning, it's going to continue reacting the uraniums, and it's going to be producing new neutrons. Those new neutrons continue going back, and so on, until the whole uranium is consumed, and that is going to make a huge energy, okay? An example of the nuclear fission is the atomic bomb. The atomic bomb is a nuclear fission, okay? And this is going to be called chain reaction, okay? So it's in the bottom. So this thing that it goes and continue reacting is going to be called chain reaction, okay? Chain reaction. Okay, so here is just an example where we have to apply our balancing. So in this case, so let's try Z, or let's try the top, okay? Let's try A. 1 plus 235 is 236, and in the other side, I have 137 plus x. There is 1 here, but there are 2 of this element, so plus 2. Okay, so this is going to be, let's see how much it is. 236 minus 137 minus 2, 97. Now b, this is going to be 92 and 52 plus x, because we don't know, no, we don't know, but the other is 0. So 0 times 2 is still 0. Let me put the 0 here so you don't believe I forgot that. Okay, so 92 minus 52 is 40. Okay, so that means this guy here is 40. And let me see who is 40. Zirconium. And in the top, 97. Okay, so let's double check. Again, 52 plus 40 is 92. And 235 plus 1 is 232. 235 plus 1 is 236. And 137 plus 97 plus 2 is 236. 137. Oh yeah, 236. Yeah, 236. Yes, 236 is correct. Yeah. So this is 137. Yes, 236. Okay, so it's correct. Okay, now let's continue talking about that chain reaction. The chain reaction, as I said, the protons that were, the neutrons, not protons, sorry, the neutrons that were produced are going to go back to continue bombarding, and is going to start making more and more, and the chain is going to continue expanding, and it's going to be an exponential growth. So that's where this nuclear fission gets the power, okay, because they're still growing, and it's a huge energy. Okay, another type of reaction is the nuclear fusion. This is fission. Fission means unite, bring together. Fission means to break. Okay, fission means to break. Maybe I should write here with a pen. Fission means to break. That's why we break the huge element into smaller parts. Fusion means to unite, to bring together. This is unite. Okay? Now, nuclear fusion occurs at extremely high temperatures. Now, this is the opposite. Combine a small nucleus into a larger one. The other break into little pieces. This one is the opposite. Little pieces becomes large nuclei and release a huge amount of energy. And this happens in the sun and stars. So you have here hydrogen 3 or tritium and hydrogen 2 deuterium. They come together, they make helium, and they release a lot of energy. Okay, that's why the color of the sun. The sun has that color because it's the helium. Okay, actually helium comes from Greek, that is, helium means sun. Okay, so the color of the sun is the color of helium, and because in the sun is happening those kind of nuclear fusion reactions. Okay, let's indicate this is fusion or fission, or both. A nucleus splits, that's fission. Large amount of energy are released, that's fission and fusion. A small nuclei are formed from large nuclei. This is the same, split, fission. Okay? No, sorry, I'm reading wrong. I read this from, no, it's form. A small nuclei form large nuclei. This is fusion. Okay? Hydrogen nuclei react. This is fusion. Several neutrons are released. That's also fission. Because fission produce the chain reaction. Okay, I think I didn't write this that nice. Chain reaction. Okay, and that's it. We are done with chapter 5. Okay. Okay, so don't forget to do the homework of chapter 5. Okay, and also next week there is no video. There is not going to be video. Why? Because it's going to be your first exam. You don't expect a video, but what you are going to expect is another homework. Okay, but this is only one attempt, because this is your exam. This is going to be timed, and it's going to be only one attempt. Okay, yes, okay, and okay, have nice week, and see you in the office hour. Okay, last class I was 15, I mean last week I was kind of 15 minutes late for the office hour. I saw one of you came a little earlier, like 109, something like that, but I came like kind of 1:15, and nobody else came. Okay, but anyway, I'll see you probably in the office hour. Okay, otherwise just you do homework, and good luck. Next week you are going to see your first exam. Okay, so bye bye.